I'm James Cho. I'm a research scientist here at CCA. I basically work on astrophysical fluid dynamics. Um, Basically, I solve equations. Uh, so I don't know much about observations, but we'll see. One of the things that I've been thinking a lot about is variability on planets, on stars, and also on disks. Um, since I only have a few minutes to describe or give you a sample of what I do, I chose this particular example. Has to do with the question, can baroclinic instability transport heat and generate turbulence in synchronized planets or stars or what have you? So what's baroclinic instability? It's basically the instability that occurs in any type of rotating stratified fluid like an atmosphere or oceans or what have you, that has a temperature gradient across it. And that has, under right conditions, the ability to generate weather, like you see here on the left for the Earth. Um, in fact, baroclinic instability is exactly what's responsible for our weather system in the mid-latitudes on the Earth. And what it does is it evens out the temperature gradient from the equator to pole. As we all know, the equator gets most of the sunlight, and the poles nearly none. Right? It turns out the answer to this question for exoplanet, whether synchronized or not, is definitely yes, very much so. Um, Quantitative aspects are different, but qualitatively, the same sort of instability happens. What you see here on the right is on the left column, the temperature, and then right column, something called vorticity, which is something to do with the flow itself. Okay? Um, if you try to figure out why such things occur, I won't go through all the gory details, but basically you start from the basic equations, which is Navier-Stokes, in circle geometry or whatever geometry you're interested in, depending on which system you're looking at. And you quasi-linearize, and that means decomposing the equations into a mean flow or background plus waves. This could be gravity waves or buoyancy waves. Or in last session, someone mentioned Rossby waves. So Rossby waves is another wave component to this. And what you're seeing on the left is a plot of the growth rate of such waves, baroclinic or Rossby waves. Um, Basically, it tells you where the where the phase speed bifurcates is where the instability occurs. And when that instability occurs, the growth rate tells you how fast the instability onsets. Now, that's a quasi-linear calculation, meaning most of it is done by hand, a little bit done by computer, because you have to, in the end, invert a humongous matrix, right? On the right is a fully nonlinear calculation. So whereas this is only, the left is only applicable to early times, on the right, it's applicable to any time and for any amplitude waves. And what you're seeing is jets that are placed at high latitude on the first frame, jets that are at high latitude going westward, and jets that are at the equator. Okay? And finally, if you step away from idealistic or simple situations and do a full-blown numerical calculation, this is not to sound too Trumpian, the highest, most accurate calculation done so far, okay? Um, and you see that when the planets or stars are synchronized, such as in a binary star, the jet amplitude is incredibly increased. The instability is much more violent. And in fact, you go through different types of instability, not just baroclinic, but something called barotropic. And you see an example of that at the bottom, where a barotropic instability at the tropics create of all things, tropical hurricane-like features. Okay?
All right, we're out of time for questions, but
Oh, right.
but he's a local, so come talk to him later with all your questions.
Thanks.
Okay. Our next speaker.
Okay. I can't talk about this, so we're going to need to change the slide. Oh, I have to do it. All right. I'm not Martin Spergel.
Keep going.
That's me.
There we go.
Megan Ansdell, not to be confused with Megan Bedell. That's going to get very confusing. I'm a new postdoc at the CCA, joint with the CCM. And while I'm here, I'm going to be focusing on applying deep learning to various astrophysical research problems. But today I'm going to talk to you about a question that was very much on my mind during my thesis and an area that I still work in now. And that is a question of how do planets form, and in particular, how quickly they form. So in the background is a bunch of the protoplanetary disks in the Lupus star-forming region, which is a pretty young star-forming region. It's about 2 million years old. And one of the questions that people have been starting to ask themselves in the field of planet formation is how many of these already host fully formed exoplanets or nearly fully formed exoplanets. And it's a bit of a silly question because these are called protoplanetary disks, and we think that they are the sites of active, ongoing planet formation, not the sites of completed planet formation. But that's starting to change a little bit in this field, and one of the reasons for that is observations from the Atacama Large Millimeter Array, or ALMA. So ALMA is a relatively new radio interferometer in the Atacama Desert in Chile, and it's been delivering basically orders of magnitude better sensitivity and resolution than previous submillimeter arrays. And every time this happens in astronomy, you start revolutionizing the fields that use these observatories. And that's what's been happening. And in particular, using ALMA, we've been able to start conducting these very large-scale surveys of complete populations of protoplanetary disks in various star-forming regions with ages that span the disk dispersal lifetime, which is about 1 to 10 million years. And so when we do that, we're no longer limited to the biggest and brightest disks in the sky. We can start looking at the entire population. And when you do that, and we start measuring the masses of these disks, we find that they are very low mass, much lower than we thought. The vast majority of them, even at very young ages, are below roughly 10 Earth masses of dust in them. And so, 10 Earth masses is about the size of a giant planet core, or the cores of, 2 to 3 super-Earths or mini Neptunes, which are very common. And so there's not a lot of material there, and of course that's assuming that planet formation is 100% efficient, which it's definitely not. And indeed, when you compare these dust masses to the core masses of exoplanets, that's a plot on the far right, we can't account for the exoplanet population. So one of the interpretations of this is that even at these young ages, the planets are actually already formed. And there's 2 lines of evidence that I think support this. One is that if you look at even younger disks, so these are in the upper left corner, embedded disks that are still in their infalling envelope. When you look at them with ALMA, with the sensitivity and resolution of ALMA, and use a lot of supercomputing time, you can derive disk masses for them, and the masses are much higher than in protoplanetary disks, so there's a lot more material there. And with ALMA, you can start resolving structures in the disk, and the structures look a lot like the structures that we see in protoplanetary disks that we've accounted to forming planets. So planet formation may already be occurring, at these very young disks that are way less than 1 million years old. The other line of evidence that is really interesting is if we look at our own solar system, the meteoritic record can give us some very accurate ages of the formation of objects in our solar system. And from meteoritic dating, we think that Jupiter's core formed within 1 million years, and also that the asteroids formed in the first few million years. So we're moving in this field towards thinking that protoplanetary disks may actually be postplanetary disks, and using that to learn more about the exoplanet population. So I think this is a really interesting shift in the field, and there's going to be a lot of really cool observations in the coming years. So if you want to talk about that, I'm happy to do that.
Well done. We have time for questions.
How do we date Jupiter?
Yeah, so not my field, but very briefly. So you can use I think they use hafnium tungsten dating in carbonaceous and non-carbonaceous iron meteorites. And when you do that, you can see that there are these two populations that arise and stay isolated. They arise at about 1 million years, and then they stay isolated for several million years. And the idea is that Jupiter's core formed, separated these two populations, kept them separated, and then they mixed together. So that reference is a good one. It's a very nice paper.
Okay, it's still yellow, so I'm going to jump to the back then. Yeah.
How do you get things like 10 Earth masses formed that fast?
That's a very good question that a lot of smart people are working on. Yeah, there are theories of instabilities in the disk that can form these areas where material can sort of stick around each other long enough to form things very quickly. You can look up papers on like pebble accretion and things like that. Yeah.
Hi, I'm Masha. I'm a Flatiron Research Fellow at the CCA. I'm new. And I'm a numerical relativist, so I work on solving the fully nonlinear equations governing the behavior of space-time, so the Einstein field equations. So if you have any numerical relativity projects you'd be interested in working on, please feel free to come talk to me. But what I've been thinking about lately are binary black holes and theories beyond general relativity. So we know at some length scale, general relativity must break down and be reconciled with quantum mechanics and a quantum theory of gravity. And we know that binary black holes really probe the nonlinear strong field regime of gravity. And so there's a chance that beyond GR effects could be detectable or visible in these systems. And so specifically, I've been working in theories that modify the Einstein-Hilbert action of general relativity through the inclusion of higher order terms and curvature. So specifically, kind of relevant to where we're located right now, there's dynamical Chern-Simons gravity. And so this modifies the familiar Einstein-Hilbert action of general relativity through the inclusion of a term that is quadratic in curvature. And so recently, we wrote a paper where we considered head-on collisions of binary black holes. This is kind of the first step to producing full numerical relativity gravitational waveforms and theories beyond general relativity. And so in this case, configurations where you have two black holes and they slam into each other like that are nice because they allow you to probe the ring down spectrum of the final black hole. They allow you to probe the quasi-normal mode spectrum of the remnant black hole. And so what we did is we provided values for what the beyond GR modifications to these quasi-normal modes look like. And this is useful, for example, for LIGO data analysis, where people perform tests of general relativity by looking at the post-merger spectrum and gravitational waves and compare it to, let's say, results from what you would get if you were to do perturbations of a Kerr spacetime. And what I'm thinking about right now is in-spiraling systems. So specifically, something like GW150914, which is the first LIGO detection. And thinking about, okay, well, if we think about what this system looks like beyond general relativity, and we ask ourselves, okay, how are the in-spiral, merger, and ring down modified? We can produce sort of preliminary results where, similarly to the paper that I talked about earlier, we can provide sort of details on how the quasi-normal mode spectrum is modified, and moreover, we can provide, let's say, modifications to the merger phase. And so all of this is useful for gravitational wave data analysis because currently, analyses are performed using kind of general relativity as your original model. And then you look for deviations from that. Or there are parametrized models. But the goal is to really provide numerical relativity waveforms, which are the most accurate waveforms because they exactly solve the equations governing spacetime, and allow those to be used in gravitational wave data analysis. So what I work on is sort of the numerical side of things in producing these types of waveform models. Thank you. So we have time for questions, I guess.
When you say numerical relativity is exactly solving, you mean down to the grid scale or some sort of approximate
Yes, precisely.
discretization.
Yes, absolutely. And so the code that we use is actually a spectral code. And so this has nice exponential convergence properties. And of course, anytime we present results, we give error bars given by this numerical grid.
Okay, can you fold in other effects, including gas effects, into your simulations?
So I'm a member of the Simulating Extreme Spacetimes collaboration, and there are certainly people in the collaboration that work with matter. So for example, there are people who work with accretion disks, and if you want, I can put you in contact with those people, but personally, I love black holes because they're such clean systems. But we certainly have people working on that effort as well.
My name is Sabrina Apple. I'm a graduate student at Rutgers working with Blakesley, and I'm going to tell you a bit about what I've been working on lately. So we know that star formation is inefficient, and we know that this holds at a range of scales and a range of redshifts. We also know that we must include stellar feedback in order to begin to reproduce a realistic star formation efficiency. At this point, most analytical models have, for star formation efficiency and star formation rates, have included stellar feedback as a fudge factor. The work that I've been doing lately is to test a new analytic model presented first in Burkhart 2018, which proposes a dynamic log normal plus power law PDF, which would take into account the competition between gravity and feedback and turbulence. To test this, I'm looking again at the simulations presented in Federath 2015. So there are 4 simulations, and we can get it to play. Cool. One which includes only gravity, which you can see collapses to form stars very rapidly. There's a simulation which includes gravity and turbulence, a simulation which additionally includes magnetic fields, and then finally a simulation which includes gravity, turbulence, magnetic fields, and stellar feedback. For right now, I'm mostly focusing on these last 2 cases. So this allows me to look at with and without stellar feedback. Already you can see that the case which includes stellar feedback takes the longest to collapse and form stars, and that the gas is distributed very differently in these 4 cases. So to quantify how this gas is distributed, I plotted the log normal density PDFs for each simulation. So that looks like this. This is the case without stellar feedback, so gravity, turbulence, and magnetic fields. Here I have plotted a variety of time steps represented as an integrated star formation efficiency. So how much of this gas has been converted into stars, ranging from the 0% case right before the first sync particle forms up to, for this plot, the point at which 10% of the gas has been converted into stars. And we see that we have something that looks like a log normal peak and something that looks like a power law tail, as we would expect. Here I've plotted a representative Gaussian fit, a representative power law tail, and a variety, the transition density measured a variety of ways. I'm happy to talk about what those are later if you're interested. If we then add stellar feedback, we get something that looks like this. We still have what looks like a log normal peak and a power law tail, but now we also have this interesting feature in the low density end. So this fits with what we would expect, that stellar feedback is driving the high density gas out of the high density regions and into lower density regions. And in this plot, I'm only able to go up to 6% integrated star formation efficiency just because it takes so long for the gas to form into stars in this case. The other thing that I've been doing is taking these log normal fits and power law fits in combination with this new analytic model and calculating an instantaneous star formation efficiency for each simulation at each time step. And so that looks like this. It's a little bit chaotic, sorry about that, but we have each of the 4 simulations here with an instantaneous star formation efficiency at each integrated star formation efficiency step. And really the takeaway here is that the stellar feedback case, this bottom blue line, is able to get down to roughly the expected star formation efficiency that we expect based on observation without having to include any fudge factors in this, just using this model. So I think we have time for questions.
On which spatial scales did you do this study? On what spatial scale is this efficiency defined?
So the simulations that I'm working with are 2 parsecs by 2 parsecs by 2 parsecs. And then I'm not entirely sure I'm understanding your question as far as the efficiency. I'm just using the fits that I have here.
Is this in the whole box or
Yes,
in a
yes.
small region? Ah,
Yeah,
okay,
so this is
it's
over
in
the
that-
entire box, yes.
Okay, thank you.
Yeah.
So, okay, another simple question, or maybe it's not. But I always wonder when we go from these beautiful 2D maps where you've got the 2Ds of information and you've got the density, and then we collapse it to this cumulative distribution, or no, PDF in density, which is beautiful, and you make inference. We could see morphological differences in the 2D maps. You pointed them out. They look different. And we've lost that information going to this dimension. So I'm just wondering if there are other statistical representations of those maps. Have you thought about other ways of representing differences?
The main other thing that we've talked about doing is looking at a column density PDF. So this is just a density PDF, so taking the entire 3-dimensional volume. And so one of the next things on my to-do list is to then create a column density and do a PDF of that and see if things change. I don't think we've specifically talked about any other ways of representing it, but I'd be curious to hear suggestions.
Okay, let's thank our speaker again.
So I'm Chiara Mingarelli, and I promise to stick to my time. I'm an ARS in the gravitational waves group, and I also work on multi-messenger astrophysics, and starting next fall, I'll also be an assistant professor in Connecticut. So I'm really interested in supermassive black holes, in particular supermassive black hole binaries that are emitting gravitational waves. So not only am I interested in the individual supermassive black hole binary systems, but also in the cosmic merger history of these supermassive black holes that generates a low-frequency gravitational wave background. Now, normally when people think about gravitational waves, they think about LIGO. These are nanohertz gravitational waves, and they're detected with a different kind of experiment called a pulsar timing array. So here we monitor an array of millisecond pulsars. Right now we monitor 64 internationally, and we look for small deviations in the arrival times of these millisecond pulsars. So the gravitational wave perturbs the space-time between the Earth and the pulsar, and this induces a small difference in when the pulse should arrive and when it does arrive. So you can use this to look for gravitational waves in the nanohertz frequency band. Why is that interesting? Well, let me take this big stick that I feel has been underused. Yes. So what can we learn about the gravitational wave background? So there's this really interesting early model here from McWilliams, Ostreicher, and Pretorius. Is Jerry here? I would have heard him by now. Yeah. This always gets Jerry's attention when he's talking. I'm like, Jerry's model? So this is a really strong gravitational wave background. This is really assuming that all supermassive black holes merge, that the black holes are as massive as they can possibly be. You turn all of the knobs to 11 and you get, bam, this gravitational wave background. So the reason that I say here it would be detectable by 2021, but we already know that this model is ruled out, it's because pulsar timing arrays are more like CMB experiments than LIGO. The signal integrates slowly in time. So it actually goes as the square root of the time and as the number of pulsars. So we would have already seen a 2 sigma feature in our data if this were the real model. The moderate gravitational wave background would assume that your supermassive black holes are not the most massive and they're not the least massive, they're somewhere in between, and we also allow for the binaries to be eccentric. Here, this model I think is really interesting. It was led by a student at Stony Brook called Tehu Ryu, who's now in Baltimore, and he worked with Zoltan Heyman, again with Jerry, and also with Rosalba Perna. And what he asked was great. What if all supermassive black holes stall and they don't merge? Do you still have a gravitational wave background signal? Well, the answer is yes, because we live in a dynamic universe. You're eventually going to have a third galaxy that merges with this galaxy that hosts the stalled binary. You'll have a three-body interaction. The least massive black hole is ejected, and you solve the final parsec problem. This actually only depletes the amplitude of the background by about 30%. So even if there is a final parsec problem, we still have a gravitational wave background. Now, I'm going to skip this one because the next slide is going to be all about this particular model and go to the worst case scenario. So what if you believe this new Shankar et al. Paper, well, it's a few years old now, but where he and his colleagues claim that all supermassive black hole masses have been overestimated, and really they're not that massive. Now, because the strain of the background depends strongly on black hole masses, this could have been a death sentence, right? So what if we turn all of the knobs down? What if we say that black holes are not as massive as we think they are? What if there is a final parsec problem that is only resolved through this eventual three-body interaction? You actually get a floor of the gravitational wave background. This is the minimum possible amplitude, and that's 1 times 10 to the minus 16, and we should be able to detect this in 2029 at a 3 sigma level, which is years before LISA flies. So what I'm planning on doing this year, and what I think is really exciting about low-frequency gravitational waves, is this potential collaboration with observation. So I started working with Jenny Green for the first time in 2017, and we've been in touch since, and most recently, she and Andrew Goulding and one of David's students at Princeton, Chris Pardo, worked on this paper where they had a really fun CCA story that I have 5 seconds to tell you. So they came to the CCA and they said, we found a supermassive black hole pair. The black holes are 10 to the 8 solar masses, and they're at 400 parsecs from each other, but they're super interesting. What can you tell us? And I said, I can tell you about the amplitude of the gravitational wave background. And I can go through all of these points later with you over lunch.
That someone is lying when they promise to go in time, and that's what happened.
I won't fight you.
Okay, but Kiara's around, so you can talk to her later with all of your many, many questions. Okay, our last speaker of the session.
My name is Eileen Gonzalez, and I'm a 5th-year graduate student at CUNY and AMNH, working with the BDNYC Research Group. And today I'm going to tell you about the retrieval of the brown dwarf binary 2-mass J1416AB. So again, brown dwarfs are objects that are in between stars and planets. They have temperatures ranging from 250 to 3000 Kelvin, so they are great analogs for understanding atmospheres of exoplanets. So these two objects are subdwarfs. I have been working over the past year to characterize atmospheres of subdwarfs, which are low metallicity brown dwarfs, and this pair is pretty weird. So the primary 1416A is an L dwarf, and it's unusually blue. It's not quite a field-age brown dwarf, not quite a subdwarf, so it's classified as an SDL7, and it's got an effective temperature of about 1900 Kelvin. The secondary is a T dwarf, and it is also weird. It is unusually red and unusually blue, and it has a temperature of about 660 Kelvin. So these two objects are great analogs for directly imaged exoplanets, and they have a separation of about 84 AU. So the question we want to ask with these two is, did they form and evolve together? What are their cloud properties, and what is their metallicity? And to do that, we turn to atmospheric retrievals. So retrievals are a spectral inversion technique So you start with your spectrum. You assume what gases you think are in the atmosphere. Use an MCMC to go through the parameter space, and what comes out is you have a converged thermal profile, so you can look at the pressure temperature space of the atmosphere, and then you have abundances of the gases you assumed. So why I'm using retrievals is because for these objects, we're looking at TNL dwarfs. They are covered with clouds. The T dwarf is comparable to the cool brown dwarf or warm planet, and the L is comparable to the warm brown dwarf or a hot planet. So the code I'm using is Brewster. Right now, it's the only retrieval code built to deal with clouds in these objects. And what's really cool is you also get out a retrieve spectrum that fits better than your self-consistent model grid. So in this figure, the data is in black, and the maximum likelihood spectrum is in yellow, which you can see it fits the data much better than the two model grids that are in magenta and aqua. So what do the retrievals tell us about 1416AB? So first off, 1416A prefers a cloud model. These two are indistinguishable. The winning model is a deck cloud. So you can think of a deck cloud as a thick fog where you can see through it to a certain point, and then below that you can't see anything. So in the middle, use the giant stick. This is the median cloud. So the point where you can't see below, the optical depth goes to 1, is in purple. And then the blue shading is where the optical depth then goes to 1/2. And on either side is the 1 sigma. So we can see that the deck cloud is constrained. The location's constrained quite well, but we don't really constrain the vertical height of the cloud. For the slab cloud, the delta BIC was 1.4, so they're indistinguishable. And again, we don't really constrain the height of that cloud so well. For 1416B, we see that it prefers a cloud-free model. And for both sources, we find that their C to O ratios are consistent, meaning they have formed and evolved together, and they have consistent and similar metallicities. So this is part of my larger thesis sample where I'm trying to look at subdwarfs and see the question is, are they likely cloudless? And the last thing I want to leave you with before I run out of time is I am on the job market, so feel free to come talk to me about jobs. And there's time for questions.
Very good. Okay, question. David.
So do you have data on the time variability of these dwarfs? And I mean, I'm wondering about is, do you have additional information on the clouds from the time variability?
I don't have additional information. There was a study on 1416A that was in a variability survey, and it came out as being kind of variable, and they weren't certain on that.
Yeah, I mean, this was a question actually I was going to ask James, which is, I mean, on the theory or the observational side, which is, what information is there in weather about clouds, and can we, we usually talk about weather as something that's not containing information, but if you have these instabilities and, another check of cloud or cloud-free would be the time variability.
Yeah.
Absolutely.
It'd be a great thing to look at.